Now, in this lesson, we would like to look at this discussion of the theorems of parallelograms. Now, in one previous discussion, in one previous lesson, we had a discussion on the properties of parallelogram. And we talked about the discussion, rather we talked about the properties of parallelogram, and we also saw that some of those properties have got a lot of applications that we can use to form equations so that we can use it to solve for some unknowns. Now, there are times when we may not only be required to use those properties, but rather to explain how the properties come up to be true. Okay, sometimes we are required to derive the theorems. For example, one thing we saw was that if A, B, C, D is a parallelogram, then AD and BC are congruent, meaning they are equal in length. Also, if AB equals to DC, then we also say they are also congruent, okay? Meaning they are equal in length. Now, we may be required to prove this out. We may be required to show that this is true. Now, in the event that we are required to show that this is true, we follow some steps to lead to the conclusion. Now, we also saw in one previous discussion, apart from the element of the length, AD and BC, or AB and DC, we also saw that for a parallelogram, opposite angles are equal to each other. By opposite angles, we mean angle at B and angle at D being opposite angles, and because of that, they are equal to each other in value. Meaning if this other angle is 60 degrees, then this other one is also 60 degrees. Then also angle at A is opposite to the angle at C. And because of that, we also say if the angle at A is, for example, 120 degrees, then this other angle is also 120 degrees. Now, that is what we are going to be discussing in this theorem 1. We want to prove theorem 1. Okay? Well, the thing we are going to prove is right here. That what? That opposite sides and angles of a parallelogram are equal. By opposite sides and angles of a parallelogram, as I indicated, the opposite sides are this one, the sides AD and BC. Also, the sides AB and DC. These sides occurring in pair, they are opposite sides. Then for the opposite angles, the angle at A and the angle at C are opposite angles in that pair. And also the angle at B is opposite to the angle at D. They are also what? In their own pair. They are opposite angles and they are also equal to each other. Now, when it comes to the proof, the thing we want to do in step 1, okay? In fact, let me put it down as step 1. So we say in step 1, the first thing we want to do is to connect point A to point C. When we connect point A to point C, we form a straight line, okay? And that straight line is known as a diagonal. Now, the next thing in step 1 is to connect B, the point B, to the point D. then we will also be forming a straight line, and that line is also known as a diagonal. Basically, we will be having two diagonals. In step 1, we draw the diagonals. The first diagonal when we connect point A to point C, the second diagonal when we connect point B to point D. Now, the next thing after that, we will now be having this other what? This other diagram here, this other polygon. Now with what? With this other one here. The lines are now formed. Now that the lines have been formed, we would like to label them. So we are going to call the line at A, that is rather the angle at A, because the angle at A is now divided into two, 1 and 2. So we would like to call this upper side 1 and the lower side 2. And so the lower side here is 2 and the upper side is 1. Also in the same way, we are going to call this upper side 1, just like this one, and the lower side here 2, just like this. For the what? For the angles dividing B and D. Yes, we would like to call that the second step. In the first step, we formed diagonals, okay? We formed the diagonals. Yes. Now in the second step, well, in the second step, there seems not to be much, just writing the what? Just writing or labeling the angles now. Yes, that is the next thing. We now label the angles, okay? Now, the other thing here is this. This line here, AD, is parallel to the line DC. Okay, the line AD is parallel to the line BC. In fact, I'm just going to draw this really quick. Let me find a proper tool for drawing so that I can draw really quick. All right, so this is one line. We're calling this line what? Let's make a long one like this. Okay, so this is the line forming AD. Then we can create another line right here, like that. Okay, so these are two parallel lines. Now we are looking at AC. AC is very much like this line here. Okay. So yes, so this is now what? This is now AC. So A is at this upper point here. And what? C is this lower end. Now, notice that this angle here, at this point, this other angle, this angle here, and this other angle here, they are alternate angles. And also, they are equal to each other. You see that? The angle at this point here, in fact, if I could draw it something like this, yes, not the perfect shape of an angle, but it can illustrate something, and this other angle here, yes, something like that. So you see, this angle here and this other angle, they are alternate angles, and they are also equal to each other. Then now we can relate it to this. So we say angle A1 and angle C2, they are alternate angles. Why? Because this line here connecting or part which is forming AD and this other lower line, they are parallel to each other. So we say AD, okay, and BC. They are parallel lines, and because of that, we say A1 and C2, they are equal to each other by the fact that they are alternate angles. We are now talking about B. Yes. Now, the next thing is, well, there is also A. The other thing is this lower angle here, this one now, and this other one here. They are also what? They are also alternate angles. Okay, they are also alternate angles. So this other angle here, which is now called what? It's A2 from our parallelogram. So this angle is angle A2, and this other angle also C2. So we now go ahead and say, well, the angle A2 and, okay, and the angle C1, that is this other angle here, and the other angle, they are alternate angles, and they are also equal to each other. That is another property. We get it down right away. You see? Now that is what? That is A. That is not all. There is one more thing. This line here, which we are calling AC, this line, okay? This line here, AC. This line forms the two triangles. Now, notice that there are two triangles here. The first triangle being triangle A, B, and C. The second triangle being triangle A, D, and C. So yes, there are two triangles of interest in this first case. The triangles of interest. If we first ignore, if we leave this line BD, if we pretend that the line BD does not exist, that means we are only having one diagonal, AC. And with this one diagonal AC, we can see for ourselves that A, B, and C forms one triangle, and A, D, and C forms another triangle. But they have a common what? A common line, AC. And because of that, well, the AC for this triangle, ABC, is equal to the AC of the triangle ADC. Well, once again, AC is part of the triangle A, B, and C. Then AC is also part of the triangle A, D, and C. So, well, we can say this AC, which forms triangle ABC, is equal to the AC, which forms triangle A, D, and C. And that is the other property that we have here. Yes, that is the property that we have. And now it's under what? Common side. It's a common side to all the what? To all the two triangles. Now, with all that said and said and put down, we can move on to one more step. That is, when we look at this triangle ABC and ADC, we can confidently then say, well, the two triangles are equivalent. Rather, the two triangles are congruent based on another property which we call SAA. SAA represents side, angle, and angle. Okay? So this then means if you have two triangles with a side, okay, with one side being the same and two angles being equal to each other, okay? then the two triangles are considered what? Congruent. See that? So yes, that is the next property which we will use. And this comes from, well, the SAA we can write here. You can even see for yourself the test for SAA. Now, one thing we notice here in full statement is that if two angles of triangle ABC, okay, are equal to the corresponding two angles of triangles PQR, then the sides and the sides not included by the respective pairs of the angles are also equal, then the two triangles are congruent. Well, that's a long statement. Let's just look at the mathematical illustration, which is right here. If you have two triangles, A, B, and C, then another triangle P, Q, and R. Now, if one of the three sides, okay, we are talking about triangles with three sides. If one of the three sides have got the same length, or they are congruent, and the angles, like in this case, angle at A and angle at P, then also angle at C and angle at R, if those angles are also equal to each other, then we say that this triangle here is congruent to the other triangle. Well, now relating to the other first triangle of ours that we are dealing with, we are looking at what? We are looking at ABC and ADC. Now, apparently, this does not look as closely related as the other one, but if we flip over, if we can flip the triangle ADC, so that A would come down, C would move up, and D turned a little bit, you soon notice we have a shape similar to that of a kite. And we can, you know, conclude, we can compare and see that, well, by SAA, the two triangles ABC and the other triangle CDF, they are what? They are congruent. That then leads us to conclude that therefore, the length AB, which is this length here, AB, and the length CD, which is this length here, they are equal to each other. And secondly, the length AD and the length BC, they are also equal to each other. Now we can go one more step and say yes. Also for that, the angle at B and the angle at D, they are equal to each other. And finally, or similarly, we can also prove in the similar steps, starting from where? Starting from here, of drawing the what? Of drawing the diagonals. Using the same steps, A, B, C, D, up to this point, we can also prove that the triangle ABD, that is using now the second diagonal, because the first diagonal was enough for us to prove that this length here, AD and DC, rather AB and DC are equal to each other, BC and AD also equal to each other. We were using only this what? This single diagonal. Well then, if we put this second diagonal and for example, we remove this first diagonal AC, then using these similar steps, we can show that the triangle A, B, and D and the triangle B, C, and D, are also congruent triangle. And because of that, we can also conclude that the angle at A in general, which is this one here, and the angle at C in general are also equal to each other. So this is the first theorem. And I prepared it separately that you can what? You can go through and, watch again if you find that a step is not very clear. Now, in quick summary, this is what you would do to prove that AB equals to what? DC and AD equals to BC and the other two angles. Well, step one, draw a parallelogram, or at least extract the one which is already drawn for you. You use the one already drawn, only that you draw a similar one. And you name them the same way, A, B, C, D, the way it's done right here. Okay? Then you draw one diagonal. One diagonal could be enough for this. So draw one diagonal, which is what? Which is AC. In this case, you draw one diagonal like that. Then when you draw one diagonal, steps begin to flow in. Okay? You begin to label the what? The angles. This being, for example, 1, and so this is 1. Rather, this is 1 up here and 1 up here. This is 2, 2. That's enough for that. 1, 1, 2, 2. That's enough for that. Then the next thing for you is now to use the relationship from the fact that this line here is parallel to the other line. And because of that, this angle here is equal to the other angle since they are alternate angles. Then you also want to look at the remaining angle, which is now this other angle and what? And the other lower angle. Well, it turns out that these two angles are also alternate angles. Then the third thing you want to look at is the what? Is the common side, which in this case is side AC. They are equal to each other. The AC forming the first triangle equals to the AC forming the second triangle. That is because they are common sides. You make sure you state the reason for your claim. For example, if you say A1 equals to C2, well, what is your explanation? The explanation or the reason is that these ones are alternate angles. Then the next thing is that A2 equals to C1. The reason there is that they are alternate angles. Then now, the other thing is what? The other thing is to look at the common what? The common side. So you say AC for the first triangle equals to AC of the other triangle, basically saying AC equals to AC. Why? Because it's a common side. It's shared by both triangles. Then the other thing is by the fact of SAA, okay, side, angle, angle, or you could call it angle, angle, and a side. SAA or AAS. We can also state that the two triangles, these and these other triangles are what? They are equivalent or simply congruent triangles. Then we conclude that the length AB and BC are therefore equal to each other. Also the length AB and CD also equal to each other. You see that? And because of that, this other angle at B also equals to the other angle at D. And that is it. And that leads us to what? To the conclusion of our discussion of today on Theorem 1.